Hi. So I am John Brunhaver, and we're going to continue with our building a rasterizer. So what I'm just doing right here is I'm just going to try and build a quick and dirty figure to kind of walk through what we're working on today. So if this is your first time joining us, the premise of the stream is that we're going to be building a rasterizer. And so what a rasterizer is doing is it is figuring out which pixels are covered by the triangle. And so we started out by saying, well, let's build a bounding box for the triangle to figure out which pixels we might look at. So in this case, what we're kind of interested in is, and then my snaps are not working the way I would like. There we go. What we're interested in is figuring out, well, which sample should we test? And so to do that, we sort of said, well, let's just look at the samples that we happen to cover, that the bounding box happens to cover. So the problem is, and let's build out our pixel grid. So what I'm drawing here, quick and dirty, is a representation of pixels. So a pixel kind of is this square region that we're going to consider illuminated, and then the little red dot. So it's the sample we're evaluating. So is this something that we should test or not? So we could draw, let's draw a green triangle. So we're kind of interested in, which sample should we test for this triangle? And so we can evaluate all of these pixels, right? As we could kind of go, well, let's look at all the pixels on the screen, but we kind of want to limit it to the ones that really matter. So in this case, what we're hoping is that we luck into evaluating the ones that matter. Now the problem is a pixel is a region, and if we were to get the best answer, we'd sort of integrate these triangles and go, well, partially this triangle covers this, but that's really expensive. Instead, what we're going to do is sort of say, if the triangle happens to cover this sample point in the middle, then the pixel is fully covered. So this would be fully covered, this would be fully covered, and this would be fully covered. But these would be uncovered. Now, if you're thinking, well, that's probably going to look awful, depending on how big the pixels are and how small the geometry is, it all matters. For the electrical engineers who are watching, this is akin to sampling error. Is that this is Nyquist sampling issues, and that you are trying to sample something at far above the rate that it's actually occurring. Right? Is that this geometry has an infinite frequency at its bound because it's an infinite stop, and so you're just going to have aliasing errors if you don't pre-filter. And because it's geometry, you can't really pre-filter it easily. So going back to our rasterization, we were going to draw a bounding box around this. So we might draw, this box around the triangle. Oops. So our box is a little bigger than it needs to be. There we go. And then let's see. Can we pick a good? We'll, there we go. So that's red. So our bounding box is red. So what we kind of want to do is only ask for the samples that are inside the bounding box. So what that means is that we would only like to test these 6. We don't want to accidentally test these guys. We don't want to accidentally test those guys. We just want to do these 6 tests. So what that means is that if this is our lower left corner, so in graphics, the top left of the screen is the coordinate axis for 0, 0, and this is our upper right. What we want to do is we want to ceiling the lower left, and we want to floor the upper right. And so that's the next thing to work on before we get to our iterator. So the next thing after that is something that'll iterate over these 6 points to build our triangle. All right. So this is our test bench from last time that was doing the bounding box. So now we're going to build a new unit. So we'll call it, clamp for kicks. And to make my life easier, I'm gonna copy my bounding box, and we're gonna call this unit clamp. And then we're gonna copy our top under bounding box, and we're gonna call that top under clamp.vp. All right, so that's not too bad. So we can just open those. All right, so we should do some cleanup. So this isn't bounding box, this is clamp. So 2 vertices of d dimensions, and we're going to find the tightest bounding box for the samples we are interested in. So for static sample points, we want to clamp to the sample grid. And we will, so lower left should be ceiling, and upper right should be floor. Perfect. So let's look at our parameters. So we don't need these vertice things anymore. We do need the dimensions, so we're going to have 2 dimensions. And instead of having this loop, now we know that we're going to have exactly these 2 points. And we should give one an vert LL. Then we can call the other one vert for right. Oh, we actually have the names originally. Box LL, box upper right. Then let's make sure those labs. And then we should just clamp box and clamp. Cool. Let's see, D and B. And then we probably need the bit that we clamp to. And we'll say that this is 8. So clamp to the nearest whole pixel. So we said earlier that in our 22 bits, that the top 14 are pixels, integer pixel locations, and the bottom 8 bits are subpixel locations. So if we clamp to the 8th bit, so we round bits 0 through 7, and then we round to this 8th position, we should have a clamp on the right dimensions. All right. Alright, so this looks good. This looks good. Alright. So $I equals 0, $I less than $D, $I plus plus. So looping over the dimensions. Tiny for you guys. Alright, so let's see. So we said that the upper right was a floor operation. So that means that we can take more or less bbox upper right, and we can say that bits $D to -1 to, and then so we'll say 2-bit $C are the same. And then we're going to concatenate the rest with zeros. And so how many zeros is that going to be? So if that's bit C, so then we need C zeros. This should be a floor operation. Good. Now the other one is a bit more complicated. Because in order to do the ceiling, what we're going to do is we're going to add 1 minus the smallest thing and then floor. So we need a temporary for ourselves. So we're going to do this guy. We're going to call that temp. We're going to say that it is this guy. Let's see. So we're going to take bbox LL. This is take $I. Good. So we accidentally had $D here. This should be bit because we're doing bits. And then what we're going to do is we're going to take bbox LL. I, and we're going to add it and so the first one is going to be $B minus $C, take 0, so that many zeros, and then $C ones. That sounds about right. All right. Sorry, just some alarms to remind me that go off every day at 6:15 to remind me to go home. All right, so now that we've added that, so it should overflow, not overflow, but it should I'll pop the number up. So now we can just floor this one, and then we should make sure that we're using all the magics. Great, so those are all, and these guys should also be that index. There we go. So now I can play the same clamping trip, the same floor trick for this one, is that I'm going to take this, and then I would take these bits, and then add zeros. Great. And I think that is it. So this probably seems pretty simple. Part of the reason I'm breaking this out is just to kind of go slow. Part of it is later on I may come back and play with this module a little more. So I may decide that maybe we're interested in supporting other parameters. So if we're gonna, coming back to this guy, maybe there are more than one sample per pixel, so the grid we might be closing down to might be different, and so the locations might be different. So we need to make sure that parameterization works, or maybe these locations are random. So this point could randomly appear somewhere inside this box. So that would be stochastic rasterization, and that would require clamping slightly different. So instead of flooring taking the ceiling of the lower left and the floor of the upper right, we'd actually need to sort of expand out and grab more things. And in that case, I want to keep it like here, keep this that contains it all. The other thing is that I'm always afraid that I built this a little bit wrong, so I want to be able to go run some quick tests to see what's going on. So what's going on in top clamp? So top clamp. Boo. Remapped my keys at some point. Alright, so these were clamp. Great. Let's see. Clamp. My clamp. Perfect. So we should undo some of the stuff we were doing before. So this was for my $I equals $0, $I less than $D, $I plus plus. This was B box, L equals 0, B box under UR, J equals tick 0. So the other reason that I'm breaking these up into sort of small things is it lets me sort of individually unit test them. And since it's probably been a while since I've had to produce code that kind of works right the first time, I want to make sure that I'm not accidentally building unclever things. All right. So let's see. So those guys. It also means that later on when something doesn't work, if I can source it back to one unit, maybe I go and run that unit's test again. So if a module seems to be consistently producing something that doesn't make sense, you know, it might be a good idea to go do that. All right. So $random. So this is interesting. So we have a box. So these are supposed to represent a bounding box, and then, you know, do we care what this is producing? So some of these could accidentally, you know, is it going to accidentally produce a signed number? No, so we've sort of been pretending that everything is unsigned, so we're okay for now. Later on, you know, when we go and make things signed numbers, we may need to play some games. You know, do we need to worry about do we need to worry if the bounding boxes aren't quite lined up? You know, that's probably worth doing. So how are we going to do that? So one way we could do that is we could just cheat a little bit. So we know what the leading bit is. And so we can go, well, $b minus 1 colon 0 is always equal to 0. Great. So now we have something 1 bit 0. Now we have something that is definitely positive. So let's do something like that. And then what we'll do, you know, maybe our bounding box is always going to be relatively small. So what we'll actually do, say that the upper right is always bounding box plus something. So we'll say this is, you know, modulo some number. So let's say 14. You know, maybe we should use our Perl to figure this out. So, you know, $C is where we're stopping. So we probably need to grab that variable. So we aren't going to have that one anymore. My $C equals $dot get under param. I think this was clamp bit. Whoa, Stephen Gregory, awesome. You need to make sure the bounding box is never area 0, right? Yeah, so that's awesome. So yeah, that's sort of what I'm doing here, is I'm trying to make sure that I think what you're saying is we got to make sure that the bounding box that I'm producing in the test is non-zero. There is a fun case where the bounding box is 0, where the resulting clamped bounding box has a total area that's 0, and it sort of works by if I ever have a case like where I've sort of fallen between the pixels. So let's see if I can't get it to behave a little bit. There we go. So we'll build ourselves a really tiny triangle. Yeah, so there's a fun case where if I'm between the samples, so I have a really, really tiny bounding box, the clamp would actually produce an empty bounding box. So I'd actually end up like flipping it. Right, the upper right would sort of clamp down. So let's see, where would it go? It would go to here, I think. Yeah, and then the other one would try and go like here. And so you wouldn't really have a bounding box. You'd sort of have a dead bounding box because it's empty. And so that's an actual optimization case, that if a triangle is so small that the bounding box falls between pixels, we can just throw the triangle away because we know it doesn't cover everything. But the yeah, in the test, we want to make sure that we're producing a good set of things to look at. So part of why I'm worrying about this now is that the next thing we're going to build after ClampWorks is the Iterator code, and so I want to give it good bounding boxes to play with. So let's see. So what was I looking for? $C get param clamp bit, and then we were trying to look to see what clamp bit was called. Yep, so clamp bit. So let's say that we're always going to add, C plus dollar $B C plus 3. There we go. So unless somebody has made a really tiny screen, C plus 3 is probably reasonable. So always test. So, and then because of the way that floor and ceiling works, and I think we only need to keep the $J's here. And get rid of this one. Yeah, so now bounding box lower left should be less than clamp bounding box lower left. And then bounding box upper right should be greater than clamp bounding box upper right. All right, so let's see. Does this look good? So I'm not seeing anything too bad. So let's try generating this. Module name equals clamp. So I probably worked this at some point, yeah. $J requires global symbol at line 69. Yep, because I changed my I's to J's. So we'll just make these all J's. And then we're probably fine there. So it looks like I've done this in a few places. So the perils of copy-paste code. So this is one of the reasons to use strict, is that it'll catch some of these wonky things. Cannot locate module clamp. Yeah, so what's going on in clamp? So it's expecting a $V somewhere. Yeah, so we don't need this line anymore. Great. And then do we need to keep track of, do we need a warning for dimensions? No, I think this just works. Great. Boo, okay. Has errors, okay. So it doesn't like the way I wrote that. So what we could do, we can kind of nest this, right, as we could go. This is D1. This is $D0. Right, so that's good. And what we'll do is we'll subtract like $B to D1. Great. So 100 minus 1 is 111. Good, so maybe it'll like that better. So now we have an 8D0, so we forgot the little tick that goes there. And we got lints. So this is fun. All right. So let's. Oh yeah. So we were playing this game before, where we have all these fun things. So I got rid of one of the errors that it was complaining about. So how did I do that? So before it was saying like non-void expressions, and the way I got rid of that was that I decided that that's not. Yeah. So null. It was a null statement thing. So I added a flag to my makefile that sort of says, well, if you're do not show me those lint errors. I don't care. Because I'm not going to fix those. But, you know, in top clamp, let's see if we can't clean some of those up. So instead of keeping track of this, we'll just chuck those. Okay. And maybe that'll take us a little further along. Get rid of as many of those lint errors as possible. Yeah, there we go. So, you know, just to make sure that we're lint green. A little grep for lint in the logs. We'll look for warnings in the logs. So those are the normal ones. And then any errors in the logs. Nope, that's just the lib import is error info. So that's good. All right, so we have no problems there. So now that we've compiled, we can run. It says that it ran. It gave us no output. We should be squirrely though, right? Because we didn't write a very good test. We sort of wrote, it does this. That's generally what it should do. So I would say that this is, you know, test path clearing. You know, properties of floor and ceiling. Right, and I'm sure that we could write more of these in. But more or less what I'm hoping for is like a test that's just good enough. So I'll, you know, because I don't quite trust what I'm doing, I'll actually just write a display statement for each of these. And we'll probably get like tons of them, but that's fine. And if you've been looking at a lot of the test benches I write and seeing a ton of these just print statements spooling to the output, that's the idea. You know, and I could probably make my life a lot easier if I made these B's. Because then it'll be easier to see that it floored and ceilinged. And then the upper right should be floor. This one should be seal. Perfect. All right. And then let's not forget our semicolons or it'll get sad and yell at us. That's just too many semicolons. All right. Yes, tons and tons of printing. All right, great. And then hopefully what we're seeing is that since there are 8 bits of subpixel precision, we should see 8 zeros. So are we seeing exactly 8 zeros? So we see 1, 2, 3, 4, 1, 2, 3, 4. So always And then we didn't quite. So I'm running a screen thing here, I think, from last time. There we go. So we can kind of just line the cursor up right there. And just kind of scroll down, and everything should have 8 zeros. Okay, so let's look at one of the ceilings. So does this make sense? Yeah. Because it had 4 ones over here, so it should be one bigger. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it should have gone from a 0, 1 in this position to a 1, 0 in that position. That makes sense. Good. So it looks like it works. So I didn't totally botch this. Perfect. So now we have our 2 units. We have one that finds the bounding box. We have one that clamps us to the sample grid. You know, we should, if we're being good designers, we should check our status in the repo, and we should add the things that we just built. So this is added clamp module. And so now that's all checked in. Yep, so that's all our info to check. You can see here that we're, this is going to the grading script repository, so this is all the code for the 2 classes that I'm working on. Thus the EE498. And this just ended up being a convenient place to get some work done. Because I know all the scripts are running right now because I'm taking care of them. Alright, so going back to our figure, so now we have our clamped bounding box. So, and we'll give it a new color. Not that color. So we'll make it blue. Still not what I wanted. So we'll make it, ooh, purple. Purple's fun. Or maybe like a hot pink. Alright, so we have this bounding box, more or less. Oops. Too much zoom. Alright, there we go. So, oh, not that bounding box. So now we should have this bounding box. So we have these points. So we need to build something to walk over those points. So if I were writing, you know, if I were writing my C program, there we go. Here's some Scratch. You know, I might just write, you know, for x equals lower left, x less than upper right, you know, x plus plus, and then for y equals lower left, y less than upper right, y plus plus. So I'm going to take a short break just to see what the phone calls are about. I'll be back in 2 seconds. Sorry. I guess minor emergency at home. So yeah, we would do this, and then we would emit XY to the tester. You know, or we would just call the test sample, and you know, we would give it the triangle and the X and the Y. But we can't really build this. So anytime you see a for loop, you know, think counter. Oops, so we can't save this. It's just a compulsive habit. So really what we need to do is we need to build two counters with the programmable min and max. Easy peasy. All right. So let's see. Let's see if we have anything lying around. So the first thing to build is a counter that takes the XY. So let's see, what do I have? So I do have a counter.vp. It looks like counter at some point. We have a counter version 2.vp. That's right, because there's also a verif counter. No? Just looks like for some reason I decided to call that counter 2. So, you know, let's make life easy. We're going to call this counter counter under t.vp. And maybe I even have a top. No, but I wrote a top earlier for 333. You know, maybe that's too many E's. That's too few. Great. Top under counter.sv. So we're going to make that top. And what do we call it? So we just called it counter p. So we'll call this top under counter under p.vp. Great. So let's see. So we have our counter under p. It looks like max count value equals 32. We have bit width. Great. So instead of doing that, we're going to set parameter name bit width. I'm just going to say that the value is 22. And then, you know, for now, let's do the one-dimensional version, and then, you know, see if we feel like expanding out. And I think I've been calling this $b. So we'll change all of the BWs to little b's. Great. So this counter is programmable in that it has you know, a lower bound b minus 1 colon 0 and an upper bound, and we'll call them bounds inclusive. So I think in this one you can sort of see that we were originally counting from like 0 to m minus 1. So in this one we're going to count from LB to the upper B. All right. So this is our flip-flop. Holds the number of bits. Great. Always count back in. Yes. You know, I don't know that we're, we're not really going to decrement, are we? Probably not. So we can probably just have the increment here. So we only need to worry about the increment case. Good, good. Right, so we could actually simplify this and sort of say, well, count next. Yeah, but this actually becomes pretty nested. Great. So let's see. So what else is going on here? Well, we need a way to start the loop, right? So we need a way of getting LB in there. So we probably need a new input. So there we go. So now we have increment and we have set. Should make sure that we're concatenating, because this isn't actually a multiple argument thing, it's a string. So now this is 2-bit 1 0, and then this is 2-bit 0 1, case x, count next equals lower bound. Good. So cycle after set is LB. Great. And maybe we want to have a signal to help out with when we're done. So maybe we have a done signal here. So we could just say that assign done equal to, count equals to upper bound. Great. And then I think maybe we'll, I think we may, we'll leave the increment in. Maybe the guy downstream will want to stall for some reason. All right. So cycle after set is done. Do we need to worry about this condition? We have some guarantee that LB is going to be, UB is greater than UB. So we should actually write that assert property and at pause edge clock UB is greater than LB. We could write not reset, or great. So let's see. Yeah. So we don't need to worry about this overflow condition. So we're more or less just always adding one to count. Great. So this is our set case. This is our normal case. This is our stall case. Increment every cycle. So since we're not using decrement, let's get rid of it. And maybe we want to be clever and we actually want to say done next. So next cycle we're going to be done. And then what we'll do is we'll say this is count next. This feels kind of wrong because I don't really want to operate on next signals, but we'll leave this in here and then see what trouble we get into. That's a great question. So the question in the live chat that I don't think will be visible later is the assert property synthesizable? And it's not synthesizable. It'll actually throw warnings in the synthesis flow. But interestingly, it will. So the interesting thing is that it'll throw warnings saying it's not a synthesizable construct. But on the other hand, it'll try and use those properties to optimize the logic. So in this case, it's not really that helpful to know that upper bound is consistently greater than lower bound. But one example where it's extremely helpful is with one-hot logic, is that if there is not something helping it to know that a bus is guaranteed to be one-hot, writing the property that the bus is guaranteed to resolve to one-hot at the positive edge of the clock means that it can play games. I'm not 100% sure that this is the right syntax. Let's grep property */*.vp. Yeah. So it looks like this is something I do in the LIFOs, app pause click. Yeah. Oh, that's a good idea. So I should actually add this $is unknown. So what this will, so $is unknown will return true if it's unknown. So if UB and LB are unknown, we don't really care if the assertion is true, because at that point it doesn't matter. Let's see, and then not reset. And if we're in reset, we don't really care about this. We can be in some illegal state. It's just as soon as we come out of reset, we want to be in a good state. So yeah, so not synthesizable, but important. So important that it looks like I put some in my LIFO. And it looks like, it looks like it comes up over and over again. So a good idea is if you're making yourself soft promises on your interfaces, to actually enforce those promises with assert properties. So I think LIFO is making a similar statement. So let's see. Yeah, push on full check. Is it saying, no, you promised. You promised that you couldn't push on full, and you promised that you couldn't push on empty, and so these assertions will trigger if somebody breaks those promises. So this would be helpful in making sure that the test bench is doing what it's supposed to be doing, or if somebody's using this LIFO somewhere else, and then their logic is broken. It'll help kind of point out that bad things can happen. In that case, it is something that it can optimize, because it sort of knows that these are mutually exclusive signals, and so if there's any sort of cleverness in the logic where full and empty would affect things, so if I had implemented safe versions for some reason, like push safe is equal to push and not full, and pop safe is pop and not empty, it would have eliminated that logic, because it knows that those two things are mutually exclusive. So let's see. Great. So I'm wondering, is there anything else that we want to add in here? Probably not. All right. So we also have the top under counter under p.vp. So this is, I stole the top module from 333, so it's still in Verilog. So we gotta clean this up a bit. And we'll help ourselves out by taking a peek at top under clamp. Use strict, use warnings, good, good, good. We're going to do the dot, and we're going to build out our parameters. So there we go. Generate base, clamp, my clamp. So this is counter under P. We said this is my counter under P. And then what was the parameter? It was bit width. So we're good. So we can keep. Ooh. That's an excellent question. So let's. So it may. I mean, so one thing you may want to do is maybe you want to have some custom debug statements inside your hardware. Right, so let's cheat, and we'll go, okay, just at every positive edge of the clock, just tell me what count is, and then I think, let's see, maybe that might do something interesting. %d, and then put count there. Good. So this is how I would do, a debug print statement in my hardware. So I think this might work a little bit better than including it in the asserts, but I suspect there is a way to add like an else clause to this. I don't know. Did I do that in a FIFO? So I don't think I did. Yeah. Well, this is the FIFO. That's not what we're looking at. So this is the LIFO. Yeah. So I didn't add any else statements here to give you anything helpful. I did name them. That might be helpful, and hopefully the expression is enough to get people along. But yeah, it would be nice to print something out. So we'll write something. We'll see what it'll do. So we got some debug stuff in there. And hopefully we didn't give away the punchline on the FIFO. There we go, top under counter. That's right. And then we were looking at top under clamp. So this is how we were. And we needed our generic bench. Great. So let's see. So we can keep these. Now we can probably go peek and clamp. Not clamp. Counter under P. So, and then we went. Okay. Add semicolons. There we go. And get rid of the inputs. Good, and then we need the signals from which are usually trigger start seed and clock period. Good. So now that is that guy. So we don't need the clock because we're getting clock from the generic bench. We don't need a reset because we're getting reset from our generic bench. Yeah, this might, we'll keep this, but I think I have a better version up here. Yeah, we'll call this our basic maintenance block. The one up there seems a little bit better. Fix me, great. And because we need to make these the whatever they were called, LB and UB. They were one-dimensional, so we'll actually just keep track of last count, which seems to be what's going on here. So if we're going to do that, we should probably add a last count. Good. And then we probably need to rewrite all of that. And then these tests look close. All right. So next time on Hardware Design Rast, we need to finish writing the stimulus for our counter under P. We need to rewrite the tests, rewrite the assertions for counter under P. We're going to make counter under P n-dimensional. By making it recursive. And then we need to update the tests. And then we will have a then we will have a nested for loop unit. Great. Cool. So, and next time we will get to answer Steven's questions about the dollar displays on the else statement. So, let's go. We'll go look at all these things next time. But that is about it for me today. This seems to work pretty well, so I'm going to try and do this every Wednesday at 6. And feel free to post comments in the below section if you have them. And we're getting there. We're getting there. This is a good way through the paper so far. Thanks for listening. Have a great night.